Hey, and this is joint work with Dave Pennock, Dominik Peters, and Jan Wortman Vaughan. So the problem that we're considering is one where we have a common budget or a resource that needs to be divided among M projects. And the idea is that every project can receive some arbitrary percentage of this resource. So as an example, you can think of something like government expenditure. You have this pot of money, and you need to divide it among things like education, health, other social services, defense, things like that. And we're going to take a voting approach to this problem. So we're going to have n voters who each report their most preferred budget. So other examples would be things like conference schedules. You might think about voting over how we spend our time, talks, posters, meals, things like that, how we get our energy, that sort of problem. So here's a quick example. Suppose we have these 4 voters. Each of them has reported their most preferred distribution of some resource over 4 projects. And one thing that you might think of immediately for aggregating these is to take the mean. So if we take the mean, we get a distribution like this. And many people in this room will know that the mean turns out not to be strategy proof. So if you're the second voter here, you might look at that and think, well, there's less resource going to the blue project than I want, and more to the other 3. So what if I misreport and report that I want the entire resource to go to the blue project? And now the mean will change to this, which is, by any kind of reasonable measure, closer to voter 2's true preference. Okay. So let me be a little more formal about what I mean by these voter incentives. We're going to assume that voters prefer distributions that are closer to their ideal distribution in L1 distance. Okay, so just so we're on the same page, L1 distance is between 2 distributions, is the sum of the absolute difference between each coordinate. Okay, so that's an example of the L1 distance between those 2 distributions. And we'll say that a mechanism is strategy proof if no voter can ever benefit from reporting a distribution that's not her ideal. So kind of the way to think about this is, if you can misreport and make some projects' share of the resource get closer to your ideal by, say, 0.1, then the shares of the other projects should collectively get further away by at least 0.1. So let me give you something that is strategy proof. And it's what I'll call the social welfare maximizing mechanism, ASW. And what this does is just select the distribution that minimizes the sum of L1 distances from each of the voters' reports. And this may not be unique, so let's also define a fixed tie-breaking order over the projects. So this has been studied before in exactly this setting by Shishko and co-authors. And what they showed is that this mechanism is strategy proof. So that's good, but there is kind of one problem with this, at least in some settings, which is that it's not proportional. So what I mean by proportional is that if all voters are single-minded, then the resource should be distributed proportionally to each project's support. And what I mean by a single-minded voter is one who wants an entire resource to go on a single project. So this would be an example of a single-minded profile. We have one voter who wants the entire resource to go blue, 2 who want orange, and 1 who wants yellow. And proportionality should say that for profiles like this, we should split the resource in those proportions, 1 to 2 to 1. Right? And what the social welfare maximizing mechanism will do is it will actually go with the majority. So this will go all orange in this instance. So sometimes this might be okay, but sometimes this is not what we want. Like if we're voting over how to send money to a school district, 100 parents vote for their own school to get the money, 99 vote for their own school. We probably want to split this money evenly. So that's kind of where we come in. So this is the lie of the land before our work. So the box here is the space of all anonymous and neutral, meaning that candidates and voters are treated the same, strategy-proof mechanisms. And here we have this ASW mechanism in the box. What we do is we define a class of mechanisms that we call moving phantom mechanisms. These, we show that these are all strategy-proof, and that the social welfare maximizing mechanism actually lies in here. We additionally identify one more mechanism in here that we call independent markets, and we show that it is indeed proportional. We also show that among this class of moving phantom mechanisms, the social welfare maximizing mechanism is the only that is Pareto optimal. So at least within this class, we have an incompatibility between proportionality and Pareto optimality. All right, so let me kind of get into how we do this. And first, I'm just going to introduce a new style of picture. So I'm going to ditch the pie charts that I had before, and instead I'm going to represent profiles on a picture like this. So we're going to have one column for each project, and we're going to represent a vote by a series of horizontal bars. So this 0.3, 0.5, 0.2 vote has a bar at height 0.3 in the first column, 0.5 in the second, 0.2 in the third. And so we can put more votes on there. This now has exactly the same information as a series of pie charts. But actually, I'm going to go kind of one step further and take the colors away from this picture, because we're not going to need to know which lines belong together. You can imagine mechanisms that would need to know, but we don't. Okay. So let me warm up with a known and an easy case, which is the case of only two projects, A and B. So because we want normalization here, our inputs and our outputs are normalized, this is essentially a one-dimensional problem. Right? The share of the resource that project B gets is just 1 minus the share that project A gets. And this is a very well-known and famous case that was essentially solved by Ove Moulin in 1980, who showed that subject to anonymity and continuity, the only strategy-proof mechanisms are generalized medians and vice versa. So what's a generalized median? A generalized median is a mechanism defined or parameterized by n+1 phantom values, alpha naught through alpha n. And what it returns is the median of the n voter reports and the n+1 phantom values, right? And so this is basically one-dimensional. Because I want to generalize to 3 dimensions and more later, let me also just write in here what we would output for the second dimension as well, which would be the median of the voter reports on the second dimension and 1 minus all the alphas. So what sort of flexibility does this give us? Okay, so we can do a few things here. I guess I should point out in this picture, so there are a couple of new components. One new component is the solid red lines. So the red lines are going to represent phantoms. So here, each of these red lines actually represents 3 phantoms, just on top of each other. And we also have these small black boxes, and the boxes represent the median on each column. So that's the median of the black bars and the red phantom bars. Okay, so what this picture is doing is just taking the coordinate-wise median, the median on the left column and the right column. And the phantoms, we have 3 at 1 and 3 at 0, and they're essentially canceling out for the purposes of taking these medians. We can also do something like this. So take the uniform phantom rule, where we place our phantoms uniformly between 0 and 1. Oh, I have clicker problems. Or we can enforce a half-half split by placing all the phantoms at 50-50. So this is 2 dimensions. It's nice, it's easier because it's essentially a one-dimensional problem, we're guaranteed normalization. Right? We don't have to worry about that. The minute we go to 3 or more dimensions, we're not guaranteed normalization if we do the same thing. So if we just place fixed phantoms and we take medians on each coordinate, they're not necessarily going to normalize. And there's quite a large literature on multi-dimensional aggregation, but generally they don't have this normalization constraint. So what you can do there is just decompose a multi-dimensional mechanism into single-dimensional mechanisms. This doesn't work for us. First thing you might think of is, well, how about just renormalizing the output multiplicatively? And this, rather unsurprisingly, is going to break strategy proofness. So we need a solution to this normalization problem. And what we do is, rather than fixing the phantom positions, we're going to allow them to move. And that's why our class of mechanisms is called moving phantom mechanisms. The intuition is that suppose we fix the placement of some phantoms, and then we take coordinate-wise medians. Now the sum of these coordinate-wise medians might be too high or too low. If they're too high, then we can think about moving the phantoms down so that we can decrease these medians. Or if it's too low, we can move the phantoms up. And in doing that, we can converge to our coordinate-wise medians, summing to exactly 1. Right, so a moving phantom mechanism is going to be given by a movie, or a function f, that defines a path of our phantoms such that they start all at 0, and then they move so that they're all at 1 in a continuous and monotonically increasing way. So I have an animation here that might clear that up. So the red lines are the phantoms, they're moving up. And we have our medians in the black boxes, which are dynamically moving up with them. And down the bottom, we have a number which is indicating the sum of the medians, the sum of those black boxes. Right, once this plays through, I'll play it through one more time as well. All right, so you saw that it started at 0, and then it increased, it eventually got to 1, which was normalization, and now it continues to increase. And because these things are all continuous, we can kind of show by the intermediate value theorem that it's always going to start at less than 1 and end at more than 1, this number at the bottom. So it must pass through 1 at some point. I'll just play through like the first half of this animation again. Right, so they're increasing. Soon they're going to get to 1, and that would be our output right there. Okay. So, all right, so one of the main results we have is that all mechanisms in this class are strategy proof. And this isn't totally obvious. There's an additional complication from the fixed phantom case, which is that, of course, now phantoms are moving. So in particular, their final position actually depends on the reports of the voters. So this is an extra kind of degree of freedom that manipulators would have. We can deal with this. It's actually very simple. I don't have time to give you the proof. If I did have time, I could give you the intuition in these 3 pictures. Okay, so for the kind of 6 or 7 minutes I have left, I want to show you 2 moving phantom mechanisms in particular. Those are the 2 that were on the diagram before. So on the left, we have an independent markets mechanism. And what that's doing, it's also the one I showed you before in the example. It's placing phantoms uniformly between 0 and some value y, and it's increasing the y. On the right, we're moving phantoms one at a time from 0 to 1. So one phantom moves up, then the next, and so on. Okay, so let me start with the first of those mechanisms. We call it the independent markets mechanism. So here's just a snapshot of kind of 3 points in time for that mechanism. And now, what I'm going to do is tell you why we call that independent markets. So for a minute, you can forget all this phantom stuff I told you, and I want to introduce to you a very simple market model. So what we're going to have here is we're going to have, imagine n buyers with a budget of $1 each, and we have some supply of x divisible units of a good. Each buyer is going to have a valuation per unit of the good, and they're going to just buy this good. What they're going to do is they're going to buy this good. If the price is less than their valuation, they're going to buy as much of the good as they can afford with their dollar. If the price is more than their valuation, they're going to buy nothing. That's our demand function. Right? Yeah. So we have a supply and we have a demand. Therefore, we can get a market clearing price. That's this pi star. The supremum is just to deal with discontinuities in the demand function, but this is just the price at which supply equals demand. Right? So very simple market. And what we show is that there's actually this really cool connection between the market clearing price in this market and these phantom mechanisms, because the market clearing price in this market is actually equal to the median of the n voter valuations, well, not just the n valuations, V1 through Vn, and n plus 1 additional numbers, which we can think of as phantoms, uniformly placed between 0 and n over x. So at least when I first kind of realized this, it seemed pretty magical. It's really quite easy to see. I don't have time to show you why this is, but it works out. So there's this connection between the uniform phantoms rule and clearing prices in this very simple market. So from that, we can reinterpret this mechanism where the phantoms are uniform between 0 and some increasing y, and state it equivalently. So equivalently, we can think about it doing this. It sets up m independent markets, one market for each project, and in each market it sells x units of a good, a different type of good per market. So it's a good for project A, a good for project B, and so on. Each voter has $1 in the market, and the valuation that they have for the relevant good is their report, how much funding they wanted to give the relevant project. And then what the mechanism does, it's going to vary the supply. So it can increase the supply to decrease the prices, or it can decrease the supply to increase the prices, and it will vary the supply until the clearing prices sum to 1. It's equivalent to adjusting our upper bound on the uniformly placed phantoms. Okay, so that's kind of neat, and it's perhaps some indication that this is a natural mechanism in some sense. We can also show that this satisfies proportionality. That's a pretty simple proof when you write it down. We also have kind of a third interpretation of this mechanism, which is that it's implemented as the unique Nash equilibrium of a natural voting game, a voting game that looks very much like range voting. Okay, so that's the independent markets mechanism. Let me move on and just quickly tell you about Pareto optimality. So we can show that this independent markets mechanism is not Pareto optimal. And by that I mean that it should always, Pareto optimal means that your mechanism should always output, a distribution where it's impossible to find another distribution that all voters weakly prefer and some voters strictly prefers. And as I kind of said at the start, most or all but one moving phantom mechanisms are not Pareto optimal. And the reason they're not is that we can generally construct an instance that looks something like this, where you have medians over the three left-hand alternatives. We have those medians corresponding to like a higher phantom, and on the right we have the medians corresponding to a lower phantom, and you can set it up so that the reports, a majority of voters want the left-hand medians to increase, and they want the right-hand medians to decrease. You can kind of set this up so that it's not Pareto optimal. What this picture relies on, though, is that these two red lines are interior, strictly between 0 and 1. Right? So we can characterize this as saying that if there are ever two interior phantoms strictly between 0 and 1, then our mechanism will fail Pareto optimality at some carefully constructed profile. So I guess that's kind of a pretty clear hint that the only one that we have left that's not ruled out by this condition is the one that we saw on the right of our picture earlier, where we have phantoms moving one at a time from 0 up to 1. Okay, so this is Pareto optimal. Turns out that it actually selects the distribution that maximizes the social welfare. So this is exactly the mechanism proposed by Goel et al. In 2016. Except with one, man, this clicker is so out of whack. Except for one, what I think of as a small improvement, which is that we don't actually need the fixed tie breaking order anymore. This naturally breaks ties, and it does so in favor of higher entropy. So it's the L1 maximizing, the social welfare maximizing output, the social welfare maximizing distribution that maximizes entropy. Okay, so let me wrap up with just kind of a couple of open problems from this graph. So the first one is that we don't know what lies in this orange space. We don't yet know if the moving phantom mechanisms we defined comprise the entire class of strategy-proof mechanisms, or if there's something in that space. And it would also be interesting to investigate other interesting phantom movements. So there's a lot of flexibility in how we define these movements. We've only thought about these two. There's probably others. So thank you very much. Yeah, we need L1 in the proof of strategy proofness. It really relies on, when you think about manipulations, like voters can increase some coordinate. They can kind of move some coordinate in their favor, but to do that they have to sacrifice some other coordinate by an amount at least as much. But we can't say any more than that, so it kind of perfectly matches L1. So I think we can handle, I don't think we necessarily need the utilities to be exactly L1, we just need the voters to prefer distributions that are L1 closer, right? But I don't think we can really do anything else. Maybe strategy proofness approximately stays if we are approximately L1. But yeah, so I guess that's another open problem, is any other preferences.
What are some settings where proportionality makes sense, and what are some settings where social welfare optimization makes sense?
I've thought more about settings where proportionality makes sense, and I think many settings, right? Anywhere where you don't want a small majority to dominate proceedings entirely. So I think in the paper we use school district budgeting. I can't really think of many settings where you would want 100 people to completely overwhelm 99. I think proportionality is pretty weak, and it only applies on these single-minded profiles. So it is, I think, quite a weak property.
If agents have some weights on the different issues, so if they have more weight on one issue than the other, then does this hold, or can you?
What do you mean more weight?
The distance is like sum of weight times the difference between their preference and it's weighted as well.
Yeah. I'm not sure. I would guess it will break, but I would need to think more.